Welcome everyone to this talk titled Elevate and Conquer, which is a story about our journey into kernel privilege escalation. My name is Tijme Gommers, often mispronounced. It's a Dutch name and people often call me Tijme Gommers, but it's actually an I in the Netherlands. And I started hacking when I was around, 13 years old. I hacked some stuff, learned about ethics, and then I started a software engineering study, later on a information security study, and I eventually landed a job as a red team operator at Northwave Cybersecurity, which is a cybersecurity company based in the Netherlands. And I worked there now as a red team operator for about 6 years, I guess. And besides red team operator, I also spent time on security research. And recently I focused a lot on kernel driver research, finding kernel driver vulnerabilities. And I actually do that together with a colleague. This colleague is called Alex. And Alex is actually the smart guy of the two of us. He's a former malware analyst, vulnerability researcher, and malware developer. And he actually lives in Japan. So unfortunately, he couldn't be here today, but the research that I'll share today is actually a shared research of the two of us. Now, why do we perform kernel driver research? Not only because it's fun, but also because we can learn from it and we can actually outpace the bad guys. We hope to find kernel vulnerabilities before they do, and we actually hope to get them fixed before they can actually be abused. And by doing that research, we actually gain a lot of knowledge. We gain knowledge about the Windows internals and how the kernel works and operates and how we can exploit it. So for the vulnerabilities that we find, we actually try to build fully functional working exploits, which we can then abuse during actual red team operations. So we can really let our customers experience what it's like to be attacked by an advanced threat actor that has the resources to actually perform zero-day exploitation. And this talk is actually about one of those 0 days that we identified during a red team operation and that we were able to exploit. And this driver is called JN or GN PRTDI.sys, where the JN actually stands for Juniper Networks, I guess. I'm not too sure about that actually. And Juniper Networks, does anyone know that company? A lot of people do. If you Google them to date, they actually state that they are leading in AI. I'm not sure what that's supposed to mean, because they're a networking company, but yeah. Apparently they're still busy doing a lot of AI stuff. And back in the days, Juniper Networks, together with Junos Pulse, actually created a new company called PulseSecure. And I guess many of you know PulseSecure. It's a pretty popular VPN client, used by around 40,000 organizations worldwide, I guess. But PulseSecure doesn't really, it exists, but they actually have recently been acquired by another company back in 2020, called Ivanti. And Ivanti rebranded PulseSecure to something that we see on the right here, called Ivanti Secure Connect or Secure Access Client. They have all kinds of marketing names for it. But it's basically just a GUI for a VPN and a server appliance included with it. And it looks like that on your laptop. Underwater, it's actually still just PulseSecure. The driver that we're talking about, the GMPR TDI sys driver, is actually a driver that has been in there for, I guess, 10 years or so, and it's never really changed. So, to understand what we found, I want to share some of the basics of kernel exploitation and how that is usually performed. So we'll do a quick recap on how virtual memory works in computers, but also how you would actually talk to a kernel driver and how you would perform something in a Windows kernel. Because that's important to understand if you want to understand the full exploit that I'm going to show. Afterwards, we'll look at our approach, and I'm going to show you how you actually can find, during red teaming operations or just on your own computer, how you can actually find low-hanging fruit in kernel drivers. Possible vulnerabilities or abuse paths, for example. And we'll just briefly go into this, because most of the time I'll spend you explaining how the actual exploitation process works and how you overcome typical restrictions when performing kernel exploitation. If that works, and we'll have to see if we can build a fully functional exploit, hopefully we can also show a demo of exploiting an actual system. Or if that doesn't work, we'll face utter defeat, unfortunately. So let's dive into the recap. Virtual memory and talking to kernel drivers. So every laptop, Windows OS, has physical memory, right? Maybe you've got 8 gigabytes of memory, or you've got 16 gigabytes of memory. Well, virtual memory, you've actually got much more. The Windows Memory Mapper manages your virtual memory, and every process in the Windows operating system actually has 128 terabytes of virtual memory. Now that doesn't fit in that 8 gigabytes of physical memory, so when you use more than 8 gigabytes, it is actually written to a page file on disk, some sort of cache file. Now, the higher addresses in the virtual memory range are all reserved for the kernel. So n2s kernel.exe, which is just a PE file that the computer runs, which hosts the kernel. And there's a lot more stuff in there, like the kernel drivers and other kernel stuff. Then in the middle, we have a bit of unmapped memory, which isn't really used. And the lower addresses are actually all reserved for user processes. So whenever you spawn a notepad, you'll end up in those addresses. Whenever you spawn your calculator, you'll end up in those lower addresses. And the funny thing is, those processes, so your notepad and your calculator, will actually have the same virtual memory addresses. So user process A and user process B can both allocate the same virtual memory address and host different data on it. And this is something that the virtual memory mapper of Windows manages for you to ensure that there are no collisions in memory. Now, if you want to go from a user process to the kernel, you cannot just dereference a kernel address to read data from it. That doesn't work. The virtual memory mapper will prevent you from doing that because you're not authorized to do so. So doing this, like what I show here in the pseudocode, it will just crash your program. And actually, it's the same way, the other way around. So whenever you try to dereference a user address from the kernel, that will not work. And it will actually cause a bug check, and because there's no exception handling in the kernel, it would crash your entire system and you would get a blue screen. Now that's quite interesting. Why is the kernel not able to read virtual memory of a user process? Because it doesn't have the context by default. Because if you dereference that address, how would the kernel know from which process to read the memory from? Well, if you give the kernel a little bit more context about which process it should read it from, then it is possible, of course. So then you can dereference virtual memory of a user process. Now, in kernel exploitation, you would want to go from the user process space to the kernel process space. And how that usually works in kernel exploits is by talking to certain kernel drivers that have the facility or some sort of API that you can talk to from a user process. And this is how that looks like in pseudocode. So on the left, we see our user process, which could be run as a low-privileged user. In this case, it's our exploit.exe. And on the right, we see a kernel driver, some pseudocode of a kernel driver. On the left here, we try to talk to a certain kernel driver that is able to update the BIOS. So this could be a BIOS update utility. And we just define a buffer, which is our new BIOS, which is in this case 4 pseudobytes. We define the length, and then we call a Windows API that you're able to call in your C code as well, called device IO control. And it accepts 4 and even more arguments. The first one being a handle to the driver that you want to talk to, which just, in this case, is the BIOS update utility driver. The second argument, in this case, is the 8036. It's called an IOCTL. And IOCTL actually stands for Input-Output Control Code. And this is just a number representing a function in the driver. It's as simple as that. So you need to determine which number or which function you want to talk to, or you want to call on the kernel driver and reference that number. You could compare this to a HTTP API, where you have like a /user/update or /user/delete. In this case, it's similar. And then the third and fourth argument are the buffer that you send to the driver. And then the kernel will actually send an IRP to the driver, and an IRP stands for input-output request packet. And these are basically packets used to communicate within the kernel. You could compare this to, for example, that HTTP request or a TCP packet, which contains a certain struct of data in a certain structure. Now, in the kernel driver, a dispatch function will be called with your buffer. And this dispatch function is basically a large switch statement which contains all the IOCTLs that the driver supports. And in this case, there are 3 of them. So the 72 one is, for example, able to read the current BIOS version and send it back to your userland process, so you can read what current BIOS version is installed. The second one is the one we called on the left. It's the 1036 one, which actually updates the current BIOS of the system, which you can do in the kernel, to the given buffer, which we in this case set to 4 bytes. Now usually this isn't possible, of course, because you need all kinds of authorizations for this. But in this case it's pseudocode, and this is how that works. Now we've got another one currently not implemented. So with that knowledge, let's take a look at the Ivanti driver that we identified, the GMPR TDI one, and what our usual approach is to finding bugs in these IOCTLs. Well, what we do, and this is something that you can do today, is we load the sys file of the driver, which is in C/Windows/system32/drivers. You've got all your driver files there. We load it into IDA. And you can actually use the IDA free version or the IDA Pro version if you have it. And we search for the IRP-MJ device control function, which is the large switch statement that we just saw. It's always just one function that you can look for, and you can search through the large switch statement for all the IOCTLs that the driver supports and see what they do, the IOCTLs. You can reverse them and see if your user buffer ends up in some juicy kernel function. For example, some memory move in the kernel or another function that you could abuse. Lately, you see a lot of vulnerabilities where drivers call ZW terminate process by ID, and you can pass a process ID to it, and it will terminate that process for you. And because it's coming from the kernel, you could, for example, kill Microsoft Defender. You could kill antivirus processes with it that are PPL protected. Besides loading it in IDA, we also run a fuzzer. But a bit of a smart fuzzer that is able to fuzz those IOCTLs specifically. And one of them that you can use is IOCTL BF, which does specifically that. It looks for the IOCTLs in an automated way, and it just tries to send all kinds of weird buffers to it to see if the driver crashes. And we did the same. We loaded it in IDA, ran the fuzzer, and bam, blue screen. And you can actually see here what failed. It's the GMPR TDI driver. So there must be a mistake in here. So we loaded it in IDA again without running the fuzzer, and we took a look at the assembly code. Now, if you don't know assembly, don't worry, I'll explain it a bit high over. Just assume that what I say is true. We've got the IRP-MJ device control function right here, which is the large switch statement. And first off, it will move our user buffer into RBX, the register, which is okay. We can do that. Afterwards, it will actually try to dereference that pointer, which means it tries to get or read memory from the address that is located in RBX. And it turns out that the fuzzer actually sent NULL to the driver, and so it is not able to dereference that address because there is none. And it bug checks the system, and because there's no exception handling in the kernel, you just get a blue screen. Now, even if you passed a valid buffer to it, which did contain a pointer, a few assembly opcodes later, it will actually try to dereference something again a level deeper. and it would crash the system again. So you would need to really craft a specific payload or buffer to get this working. Now, knowing that there's such poor input validation, maybe even no input validation at all, we didn't see any, there must be bugs in here, apart from the denial of service that we already found, because we can crash computers. And so we took a look at what this IOCTL that we saw and that crashed the system actually does. And this specific IOCTL code is 2018. And you can look it up in this driver of Ivanti today by just installing the Ivanti software. They fixed it, but it's a hotfix, and it isn't really applied yet in the actual main branch, the trial appliance of Ivanti yet. Here we have the assembly code that we took a look at a few slides before. The next thing it does is actually to call io_csq remove irp, which is a function in NTOS kernel.exe. So it runs something in the kernel. And we didn't actually know what this function was or what it did. So we took a look. And it turns out that io_csq remove irp can actually remove an irp, which is the input request packet, input-output request packet, the TCP packet of the kernel. It removes such an irp from the queue of the driver. And it turns out that kernel drivers have a queue of irps that they need to process, and irps can come in faster than that the driver can process them. So that's why drivers use a queue. And these irps contain actions that the driver needs to process. Now io_csq remove irp accepts two arguments. The second one being context of which irp to remove from the queue. So this could be an identifier, some sort of number, for example. Nothing really special. But the first argument is a bit more special, and this is actually a struct of callbacks. Callbacks that are called within the kernel. And these callbacks can, for example, include the callback to call when inserting an irp or when removing an irp from the queue, but also callbacks to acquire a certain mutex and release a certain mutex. So this function, the io_csq remove irp, actually helps to remove irps from the queue in a thread-safe way by using callbacks to acquire and release mutexes that you can define yourself. Now, of course, you can also use this function to do something completely else than acquiring mutexes. You could pass your own kernel functions to it in theory. In practice, this doesn't work because of some mitigation called control flow guard. But you could pass, you could, for example, use it to keep track of a counter of how many irps there are on the queue. So you could define your counter, you could define two callbacks on insert irp, which increases the counter, on remove irp, which decreases the counter, and then you could initialize the struct with those callbacks. And eventually, you call io_csq insert irp with the callbacks that you defined and the irp that you want to insert, and then the callback will be called and it will increase the counter by 1. And the same counts for io_csq remove irp. You pass the struct with callbacks again, and the irp that you want to remove from the queue, and it would decrease the counter and it's 0 again. Now, bear with me. This is how Ivanti calls io_csq remove irp. They actually use as the first argument the callbacks and as the second argument the irp to remove, but it's always, in both of the arguments, our user buffer from our user process. So we can actually define which callbacks are being called in the kernel. And this is something that we can likely exploit. Let's say we want to, for example, run a function in the kernel called hallMakeBeep, which I'm sure many of you know. It's actually when you boot your computer, it will make a beep sound. Well, this is caused by the function hallMakeBeep that is called in the kernel. So we just initialize our struct of callbacks to 3 times hallMakeBeep. The acquire lock will be hallMakeBeep instead. The remove irp function callback will be hallMakeBeep instead. And the release mutex or lock will be hallMakeBeep instead as well. So we open a handle to our driver. We then call the device IO control function with that handle to our driver, and the IOCTL that we call, in this case 2018, and our struct of callbacks. And what will happen? The Windows kernel will then actually call the driver dispatch function. The driver dispatch function will call the IOC-SKU remove erp function with those buffers that we defined. And then NTOS kernel will eventually call those 3 callbacks. It will actually call hall make beep 3 times for us. And our computer will beep 3 times. And this is actually how that looks in actual C code, which you can use to exploit this vulnerability to date. I'm not going to explain the C code. I'll just show an example that it works in a Windows debugger. So let's put a breakpoint on that hall make beep function, and let's run our exploit and see if it works. Well, it does, and we can see here that it hits the breakpoint. So we are actually able to run hall make beep. Now, if we press on the left top go again, it will continue and it will finish the userland process, and we called hall make beep, and so we did. But again, it crashed our system, unfortunately. So something funky is going on. And it turns out that after that IOC-SKU remove erp function, the driver will actually call free pool with tag, which will on our user buffer. And free pool with tag is a function in the kernel to free or deallocate a certain pool of kernel memory. Now, our user buffer isn't really kernel memory, it's virtual memory from a user process. So this will actually crash the system because there's no exception handling in the kernel. Now, as the user buffer is expected to be a kernel pool of memory, likely Ivanti never imagined that people would call this kernel driver from a userland process. They likely designed it to talk from kernel driver A to this kernel driver, or talk from kernel driver B to this kernel driver. Because then it will be a valid kernel pool of memory. So we've got a lot of constraints to actually build a fully functional exploit that does something useful for us. For example, code execution in the kernel or privilege escalation. And these are some of the constraints that we work with. So there's the free pool with tag that we need to somehow bypass because it would crash our system and the exploit would be useless. But also the free callbacks are called with guard dispatch icall, which is kernel control flow guard, which is a mitigation in Windows that ensures that the functions that can be called need to be in NTOS kernel.exe. You cannot just pass your own shellcode to it and execute it. That won't work, and it would cause a blue screen as well. And there are some other limitations. For example, that the functions that are called, we have only limited ability to change the arguments that are passed to those functions, because they reside in registers that we cannot really alter or change. And fun fact, some of the functions that you call in the kernel actually override registers as well, which would mean that the second and the third call would have different arguments than that we know up front. So there would be random arguments passed to those functions. Now this might be a lot of information to process, and I do not expect you to process this. Instead, I made a more visual slide in which we show the IOC-SKU remove erp function in IDA. And we can see here the three calls being made by guard dispatch icall, and what kind of control we have in those calls. So for the first call, we can actually define which function in the kernel should be called. We don't really have access to modify the first argument. It is actually always the address of our user buffer, which we do not really control. The second argument is always 0. That's fucked up as well. We cannot control it either. And the third argument is always our current IOCTL. We cannot control it either. It's always the 2018 IOCTL. And this is actually the same for the third call being made. We don't really have any way of modifying those arguments, apart from the second call, the middle one. Again, we can define the function being called. Again, the first argument is always the address to a user buffer, which we did not really control. But the second one, the second argument, is actually a value that we fully control. And the third one is again the 2018 IOCTL. So we need to find a function that with those constraints can do something useful in the kernel, like privilege escalation. And my colleague Alex actually achieved this by making a write what where exploit, which allows us to write a single byte to a certain kernel address that we define. And he did that by doing the following. First, we needed to bypass the free pool with tag, because otherwise it would crash the system. But actually all the code paths would end up in that function. So what he did was he defined the third function in the third callback, to a function called kxWait for spin lock and acquire, which is actually a function that accepts one argument, which is always our user buffer address, and waits for it to be 0. And only if it's 0, then it will continue the code execution. But we can ensure that it's never 0, because it contains our user buffer. So this would mean that when defining this function as the third callback, the code would never continue, and it would actually freeze that current thread, and it would never reach the free pool with tag, and thus never crash our system. So that's one problem solved, or so we thought. Turns out that calling this wait for spin lock would actually increase CPU usage by 50%. And then we've only written 1 byte to the kernel. So we likely need to do this 8 times to write a pointer or something juicy, which would spike up the CPU usage by 400%, which makes your computer unusable. But we fixed that as well by using a function called setThreadPriority, in which we set the current thread to the lowest priority, giving priority to anything else that happens on the system. And this way it would actually work. For the second call, we found a function called writeChar0 in the kernel. And this is quite a special kernel function because it actually it writes a certain byte to a certain address, but it accepts a destination address as the second argument. While usually in the kernel with memset or memmove, the destination address is always in the first argument. So this is quite a special function, and it accepts our isctl as the third argument, but in this writeChar0 function, the third argument is actually used as a counter to increase or decrease. Now, our isctl 8000-2018 is not a valid kernel address, and it would this function writeChar0 would dereference that address, but it would not exist. So it would bug check the system and crash the system. But apparently, calling device.io control to talk to the driver actually gives the kernel context of which process is talking to it, which allows the kernel to dereference this address if we allocate it in our user process. And so we did. We allocated that specific address, set it to 0, and now this writeChar0 function was actually able to increase or decrease that value on that address. So, for the first argument, it's always the address to our user buffer, which we did not really control, and writeChar0 uses it, or at least it uses the least significant byte of that address to write to a certain kernel address. And what we did, we defined a large pool of user process memory, and we used a specific offset to place it on our user buffer to define the least significant byte. So let's say we write our user buffer to 0x1000, then 0 will be written to the kernel. But let's say we allocate it to 0x1001, then 1 would be written to the kernel. And thus we control which byte is written to the kernel. And the second value, we control it fully, so we can use a kernel address of choice there to write the byte to. And then we only have the first function left that we need to do something stupid with because we don't need it. First we thought of using hall make beep. So whenever you write the pointer, the computer would beep 8 times. That was actually not really useful in red team operations. And besides that, hall make beep actually overrides some registers, which does some funky stuff with the other arguments. So instead we chose to change it to ka test spinlock, which is a function that does barely anything. It just checks if a value is 1 or 0. It doesn't change any registers at all. And so our exploit seemed to work. But there's one thing left, one constraint, and that is that we need to, the callbacks that we define, they need to be addresses in the kernel, but we don't know all the addresses of the functions that we want to call. For example, the write_0 function is not an exported function in the kernel, so you cannot really find the address of it. So what we did is we defined something called kernel pattern searching or kernel egg hunting, in which we just define a pattern of how that write_0 function looks like in opcodes, and we try to search for it in the N2S kernel binary. And when we find that pattern, we know that we found the write_0 offset, and based on that we can define where in the kernel this specific function is located. And so we did, and that worked, and we could actually try to write some bytes to the kernel. So we installed Ivanti, we installed the driver, the software, and we tried to exploit it. But then we had the biggest facepalm moment ever. Turns out that this driver is not disabled, or it's not enabled by default. It's actually disabled by default, so you cannot really exploit it. But I'll not leave you with such an anticlimax. Actually, Ivanti provided us with a tool called pulselauncher.exe, which allows you to, from a low privilege user perspective, enable the kernel driver, which should definitely not be the case. Apparently, whenever you connect from your Ivanti client to a server which uses the deprecated driver, which is disabled by default, it will actually enable it for you. So what we did, we just spun up a rogue VPN appliance, we configured it to use that vulnerable component, that vulnerable driver, and we just let the client or victim connect to that specific rogue VPN using this command we see right here, and it would enable the driver for us. So we could try to exploit again. And thus we decided to write a value 41 to this specific kernel address. And we used WinDBG, the Windows debugger, to verify if it actually worked. So currently we see 0 here. We use our exploit to write that specific byte, 41, to that address. And yes, it did work. So we could write 1 byte to the kernel. And now, from this point on, it's actually fairly easy to write a fully functional exploit. Usually you would use, you would look up the token, the privilege token of the system process, for example, and you would just copy it to your own process. And that means you would have the system privileges. One constraint of that is that you need a read primitive in the kernel, because you need to find the actual address of the system token. We couldn't do that because we didn't have a read primitive, we only had a write primitive. So what we did instead was we tried to search for our own token address of our own process, and we modified our own token manually by writing 8 or 16 bytes to it. So we ran our exploit 16 times, in an automated fashion, of course. And we did it in such a way that it enabled all the privileges on our current token. And with that, with all those privileges, you basically have a full privilege escalation. So I'm going to show you a demo of that right now. So here we've got a Cobalt Strike interface, which we currently have 1 beacon running on. We can actually make it sleep 0 and then run a whoami, which will show which current user we are, and it will also show the privileges that are set on the process. So in this case, we have exactly 5 privileges set, and only 1 of them is enabled. So we are really in low privileged context right now. So we'll run our exploit that will enable and set all the privileges, which is the pulse-esc privesc beacon object file in Cobalt Strike. There you go, it worked. It says we've acquired all privileges, and it was able to find all the offsets that we needed to the functions that we needed to call, and it wrote the 8 bytes. And now we're going to run whoami again. And there we go. All privileges set and enabled, and we are now basically system, or we can now steal the system token. So, that was the presentation. We've written a full blog post of all the details that you can read, if you want to read it. And with that, you can actually build a fully functional exploit as well. So this blog post is now live. Thank you very much. Not sure if there are any questions from the audience. I think there's a mic coming your way.
How long did your research on that vulnerable begin, right? And the overall exploitation phase on writing the exploit. How long did it take you?
To actually build the fully functional exploit? To find something juicy in a kernel driver, I think it took us a few research weeks to find like the interesting drivers that we thought were vulnerable, with about 2 or 3 persons. Then building a fully functional exploit like this, it actually took quite a while. I don't even know how many hours, but I guess several weeks full time to build a fully functional exploit. This is something that my colleague Alex did. And then I think 1 or 2 full weeks to build a beacon object file for Cobalt Strike and other C2 frameworks, including making it so stable that anyone could use it. So all our red team operators can use it as well. Yeah. So quite a while. Yeah. Any other questions?
Okay.
All right. Then thanks again.